his vice president texted me and said, well, this summer symposium has this living at the topic, and then he said, well, you are talking at giving that IS2ED on the IoT security. So, here I am, just trying to deliver. But just this morning, I thought, well, I want to add a little bit more than security. So it's a sudden change in the topic. I add a little bit about the ULP, which is the ultra low power. And I kind of look at and say, well, we are semiconductor association, and people out here are very much related to the semiconductor industry. So I keep looking at it and say, well, semi is the fundamental materials for all the fancy things, your cell phone, but what are the IoT, what are the fundamental in IoT implementation that actually will relate back to semiconductor? Security is one of them, so that's the previous topic I gave earlier this year. And I add ULP, which is an ultra low power, and something that matters to the semiconductor industry. So first I'd like to talk about the news on health. So recently there are security concerns in the airline. You've probably heard of the LG. So LG has this smart TV that have a couple cameras right in front of the TV panel that actually be able to do interactive, with your remote. But once it's hacked, this is in the news. So the LG Smart TV cam, after it being hacked, it starts unauthorized spying the people. What you're doing in your living room, your bedroom, and send this data to someone. So that broke into the news, and people say, hey, this smart thing is really not that secure. And recently, there's also the BBC news say the smart fridge. Now, if you go to buy a refrigerator, you can select the real smart one that have multiple, built-in IoTs. And the fridge was somehow hacked, and it connected to your Wi-Fi system and get all your contact and start send out the spam email. So that's also in the news. I think I don't have that slide, but that's most recent, the baby monitor. So now you have this IoT-based baby monitor, basically can look at your baby's face features, the voice, and collect those data, and then send this data to the cloud and do data analysis and figure out how's your baby's behavior. So they actually give you a warning 5 minutes before the baby gonna cry. Things like this. So it's not your normal baby monitor, but it's really, really small. Combined with the big data and cloud processing power, it is doable. But the problem is, this is the recent news, is that this, I don't want to name the brand, actually it's a quite famous company, that these baby monitors get hacked. And then the monitors start to yell profanity to the baby all day long. So you're in the office and you feel, how come my monitors, the light keeps flashing? Actually, it was talking. And it's talking, bad things to your baby. So there's another example of security gets broken down in the IoT application. So everybody is really, the IoT is the word of the year in 2014, or probably this year also. But everybody's get excited. I'm excited, you're excited, IoT. But who are the most excited people? The hackers. And let me tell you why. First, we look at say, what are those IoT? I mean, IoT is such a kind of a name that actually nobody knows the entire thing about IoT. So really, there's different segments in IoT. This again is just my kind of look at things. But different people actually give different segment and category. There are wearables. People consider a high-end kind of IoT. The smart home, the healthcare, which is really a big one. Automotive now have IoTs. Smart grid is probably the most practical IoT because it's already in industry IoT is already actually in production, and of course associated with other essential home entertainment system. So those are all IoTs. But if you look at all these things, there's something in common. Okay? compared to the legacy system. One is that they are more intelligent, they're smarter. Okay. The second one is they are all connected. And then the third one, which is often not emphasized, is the open nature of IoT. Because if you're going to bring a new device to your home, you'll be able to connect it right away. It's not something that's pre-built that have a lot of proprietary systems, so it has to be open, right? So you can easily understand the intelligent and the connected part. And then the open part is where they bring the challenge in the security, right? Even though you know that most of the sensors and the legacy system are okay in handling security, with this openness of IoT, that's where the security issue become obvious. So there's many threats into the security of IoT. Cloning, apparently, is probably the most popular one. Privacy infringement, and this is a little beyond actually security. Privacy is slightly different topics because it's about ownership of data, not necessarily the security itself. Again, it's part of the threat in IoT. The last one is actually interesting because when you have a very secure, like a server, a data system, they usually are locked in a huge server building, the data center. So physically, they are not exposed to outside. Okay? IoT is where that you actually have this called physical attack, temporary, and that's where you have consumer device, you have people breaking your house and do things like that. So you actually need to add another layer of security to anti-temporary. And that leads to my key topic, is why our IoT device is more vulnerable than ever. Okay. First, IoT is a smarter device, but not smart enough. That's the problem here. I mean, security for a computing system is a well-studied field. Okay. And there's many layers built in the last decades. It's actually quite secure. Now, the so-called to be smart IoT is actually very, very not that smart compared to our legacy computing system. And that's where they're really lacking of the sophistication of the conventional computing security. Okay. I don't know, is anybody here actually design an IoT device application, putting things together? Take one of the reference board that the guys, the silicon vendors offer and put things together. What I realized is gazillion startups in the Valley, they're mainly software focused and they just need a hardware platform to build their IoTs. And if you look at their development process, it's actually is not even close to the richness of a regular CPU silicon designer. Okay? So the process has a lot of holes. You talk about later on, I will mention the supply chain attack and all these things. So it's really a very ununified development process. And an IoT device is also very small and limited by usually the memory footprint. So you can't really have a very large OS installed in an IoT device. Usually it's embedded, something like embedded OS. And that also welcoming a software attack. The second one I actually mentioned a little bit is the unprotected physical exposure. Smart city is one of the IoT topics, right? So they put sensors in every light poles in anywhere. So these sensors and the lead, they call it the leaf nodes of the IoT system are actually exposed to everybody, exposed to human, exposed to environmental hazard. So those are exposure. We're actually also welcoming a physical template of the device. I remember that decades ago that there's a hacker that I know. Yeah, so I had a lab mate that is very like the hacking things. And he told me that's before the Sun micro system. He said, any machine I can put my hands on, I can hack it. as long as I have physical, and so that's where the physical exposure of the IoT device to the external world really makes them even more vulnerable than your huge data center in the security sense. And the last one is really from an application side. Not all, but a lot of IoT devices have pretty long product cycle. It's not like your phone, you upgrade every 2 years. Those sensors you install in the city, you expect them to last 5, 10, or even. And then there's, they may not have periodical field, we call it firmware upgrade. As a matter of fact, during the process of firmware upgrading is a golden opportunity for hackers. Okay? So that's where even you do it, you still have to cross the field and do all this, what kind of attack. So these are the natures of your IoT device that we see that they are more vulnerable than your conventional computing system to security issues. So people have put a lot of thoughts to make the IoT device a bit more secure. A lot of software development is already, these are a couple layers you look at it. You can always do the key generation. It's very familiar, right? You have rookie, you have the crypto engine that you can do that. And you can also have a so-called a virtual isolation. You probably heard of the like the trust zone, virtual kind of virtual platform for your processor. And I think the last one, which is the secure communication, that is probably the biggest challenge in implementing the security layer for IoT, given the different segment and application. You have Apple's iBeacon, which is virtually a leaf device talks to the cloud directly. And you have Intel's called the Intelligent Gateway, which likes to connect this leaf device to in some gateway before it's sent to a server. And then even that, in this model, you have Intel's, you have Oracle system, you have the TI's. There's so many different gateway. They all use different protocols. So there is no so-called standard, a uniform security. And that is really the issue is. So I want to give one example of how you actually do something in your hardware, okay, to reduce the amount of security risk. This has happened to be an example. They use the Tensilica's extender core. So if you are trying to say, I want to avoid any software attack, then you add a little bit. We call it the basic crypto. Okay, but if the side channel attack is your concern, I don't know if everybody understands. The side channel attack basically is a reverse engineering by looking at the data and to figure out what might be your architecture is, right? So maybe some of the silicon designers know that they can look at your power noise, right? By from side, they can do some instruction, read and write, and do some particular application, and look at your power noise and figure out maybe what your internal instructional structure is. So the side channel is probably the closest you can get attack a system without physically touching it, right? So then you need to add a more extensive, we call it security layer, extended security instruction to protect that. The last one, which is probably the most difficult one, and it takes the biggest hardware resource, is actually to add extensive security extension to block the anti-tamper, which is a physically touching type of thing. Some of the defense project is that they will self-destroy once they realize it's physically tampered. A lot of scramblers in different ways. So it is actually be at a cost of your additional hardware. So those are not for free. So if you want to buff it up to be more defensive to different sorts of attack, you actually need to put more resources in silicon, which is good. If you're in the silicon industry, every single bit that added to the silicon is revenue. So this is particular to the instruction set, which is the processing or process core. But there's more than just the core, the instruction set. You also need to look at the other IPs associated with the IoT need to be coming together to protect your overall security. Okay? Cache is always there with CPU, and you need an encryption, decryption, and you have memory scrambler. It's commonly used, but now for IoT, people think about you probably need a memory scrambler so that people cannot recite channel attack. Right? And direct memory access, you need to secure direct memory access, BSC programming, and secure monitoring. And do I have another one? Yes, manufacturing. Manufacturing is related to the supply chain attack. Basically, how you can anti and reverse engineering, right? And trust design house, I mentioned that a little bit because in US we have a IBM foundry, which is called the trusted foundry. So most of the high security manufacturing is done in there. As less and less trusted foundry become available, so manufacturing actually is being done in the commercial foundry like TSMC's and other things. How you gonna be able to have anti-supply chain attack? There's another issue that could be done. Having some sort of hybrid trusted and non-trusted foundry that to be integrated in multi-die SIP type of format. Okay, so that is security. So I like the short summary is here is that security adds another layer of requirement for IoT. And ultimately it leads to a silicon content increase at a reasonable cost. And that will reflect into opportunity for semiconductor companies, because that's how you're going to do it efficiently in the IoT domain. That's can be your differentiation. So I move to another topic on the IoT. I keep thinking about semiconductor takes care of the fundamental of technology. It's like you make the rubber for the tire. Ultimately, it's in a sexy Tesla car. But you can talk about that Tesla car, but ultimately, is the material provided that have this fundamental technology enable the whole enablement. So the other thing I think from just process technology and design technique point of view, as fundamental to IoT is called the ultra low power or ultra low energy, as a matter of fact, requirement as fundamental requirement for IoT. You probably heard of the kind of the energy harvesting requirement for some of the sensor network. It all really come down to ultra low power. I think, as a matter of fact, the right word should be ultra low energy instead of power, because I was displaying this layered coordination layer in a very typical computing structure. So you got this standby, we call quiescent system, which is 100% off. And really you need to be nanowatt, very, very low power consumption for IoT device. Otherwise, this whole thing is you're gonna go change your sensor battery every day or charge this. It won't be applicable. Now this got then you move to the second cognitive layer, which is called monitoring layer. It's the activity of interest. And how you look at the activity of the interest, and those are really a 2% of the entire duration-wise. It's 2% of the entire operation, and it requires somewhat a microwatt type of energy consumption in order to make sense. And then it goes to a system level processing as your typical CPUs. You go to your app that goes to the application processing with the Fabric, which is a big system that consume. It actually active a very short period of time, but it consumes relatively in 100 to 10,000 microwatt. It's a typical SoC now that you see here. And of course, you go to the whole processing, which is very, very, we call active period is very, very low. But during that activity, then you actually need a very, very high power, right? So You look at here is because of different layers of cognition, and you try to say, what does my IoT device fit in here, and how I'm going to do my design so that it will be ultra low energy. And I think that's the circle is really where the IoT sweet spot is, right? And I want to kind of open up a typical IoT system and to see what's in there, right? SoC drove the whole mobile proliferation, right? Now you can have a cell phone as powerful as a computer. SoC is huge. You look at IoT, how is IoT and SoC fit together? So if you open that, you have the processor subsystem is always there. You have one processor, usually, even a heavy CPU, depending on what level of IoT that you engage. You have this PB and SI, which is called peripheral bus, usually the sensor interface. And you have sensor itself, you have both voltage regulators and things like that. You have flash memory for a lot of automotive applications. You have some sort of analog component, ADCs and things, transmitters, receivers. And you probably have some RF to do your interface communication, whether it's Zigbee or Bluetooth or even Wi-Fi. So, but you look at here is how many of these things are really in your so-called SoC. Okay, you probably have a die one. You can easily integrate your processor subsystem with your PB and SI, no problem, right? You could stretch out and have your RF built in, but think about that. You can have another die that manufacturing in much mature process node, probably suitable for analog design, high voltage flash, and some sort of custom flow you put together, and that's your die two. You can try to put these two die together, but really the processor itself is a very, very small area. The rest of the RF and low power and flash is really much bigger area. So it doesn't make, sometimes it may not make sense to put this together, right? And the sensor almost has to be a different process node, different die. So what we talk about here is you maybe look at heterogeneous integration instead of SoC. And you probably, for the IoT, you probably need to go to a very low cost type of heterogeneous integration. May not be these sexy, 3D TSV, but it could be some sort of 3D that putting together that fits the bill of a typical IoT leaf device, but still be able to put in all these typical components together. I talk about this is I talk most of the IoT startups, and they just, I bought this system from ST, I just built my things in there. It's okay, we got 100 million of IoT startups. But think about 10 years from now, the market will consolidate, right? Who will be the survivor? When it comes to a massive scale, cost always is an advantage. Assuming you have a killer app already. So this is where that you actually, your sustainable business model here, is that you can find an internal design. Maybe your first prototype is some sort of thing that you buy from a reference board from a market, you can build in that. But ultimately, when you're massive enough, you're dominating the market and you have high volume, that's where your cost become your competitive edge. That I mentioned here is that you need to go through these type of integrations that you can achieve like ultra low energy. And you actually will be the winner when the consolidation of the IoT market starts in the next 5 to 10 years. So it's really looking ahead. This is the ultimate technology that can help us to work, right? So low energy processing. There's probably more element than just the heterogeneous integration. There were other things involved to make your overall IoT processing be low powers. There's, of course, have algorithm involved, different pipeline design instruction set, microarchitecture. You heard a lot of microarchitecture was designed dedicated for IoT applications. Usually they are very, very long pipelines with much lower frequencies. It goes to the even implementation level of work, how you put the lock together, synthesize and summon. I probably have an example of one of the work. Yes. So this is one example work that my group did a couple of years ago. So we pick anything. We happen to pick a process called Extenta. We look at it and say, well, how am I going to be taking this entire processor and to see how low that is still how low in the energy consumption can go, but still be functional for the application we're talking about. Right? So we run into these huge so-called large operation voltage scaling. It can working as low as somewhere around 0.5 volt power supply, and it goes as 0.8 volt, and with very wide frequency range, you can go as about 1 gig, and normally probably working at somewhere around 10 to 100 megahertz, or even 1 megahertz. As a matter of fact, it's some of the data we will realize. I give probably too small for you to see here. These are some of the detailed work we did for this one about how we put this process and things together. It's a TSMC process we actually used to do this experiment and be able to achieve this is a very critical numbers. People talk about what is the microwatt consumption per megahertz. This is like if you can break that microwatt, and if you really go down to a nanowatt range, that's sweet spot really here for a lot of sensor deep nodes in the lowest calculation layer of your computing. Right? So that leads to the summary. I think what we care as a semiconductor company is that there's many things. There's 90% of IoT activity maybe not related to software, may not have nothing to do with semi, but we care about what is in for us. I think security and ultra-low power are the two fundamental challenges in IoT. And these are the two areas actually silicon can play a fundamental role. So anything that you think around that is like, don't get dragged into the whole IoT or the other sexy part. If you're a silicon guy, look at it, what as a silicon guy can do to actually make the IoT better or add competitiveness to your IoT company. The second things I think of is I mentioned the heterogeneous integration in silicon, right? And it's probably, we talk about the Moore's law all the time, and we have been worried about the death of the Moore's law for the last, 5 to 10 years. It never died. But the good thing is, in IoT, actually, heterogeneous integration I mentioned, it could play a bigger role, or matters even more to IoT than the traditional process scaling, because of the nature of the component in your IoT are so diverse. It's not your digital-centric gazillion, billions of transistors and gates in a single SoC, but it's more different nature of devices, sensors and all that stuff. And that maybe come to some sort of heterogeneous integration, lower cost heterogeneous integration for the silicons that fits the IoT bill. Last one is that related to the designer here is that if you're doing silicon design, you'll probably see the design methodology gets bifurcated into quite different IP and tool flow and silicon nodes. Kind of branch out into different directions for general purpose, like CPUs and mobiles and things, to a special ultra-low energy devices, with, of course, a specific security implementation that fits the need of your IoT application. Yeah, so that will conclude my talk. Thank you for the attention.
Thank you very much, Brandon, for the talk. So I learned a lot, and I feel like I do have a lot of future in the semiconductor industry. Yeah, so we have time to take like a few questions. So if you have questions, please line up in the mic.
Hi, I have a question. So looks like IoT is a very wide field, different application and product. Is there any effort to standardize these security across different type of IoT? Particularly like you mentioned, there's so many techniques involving security measures, including self-destruction, which is really amazing. I never heard that before. So, and my second follow-up question is who can drive that? Would that be a company, professional association, or maybe the government?
Yeah, I love standardization because a lot of people in the so-called semiconductor ecosystem like standard because that's where that you can thrive, right? Because different partners can come together and work together. Security is actually from historical point of view, is a difficult part because there's never a standard for security. We feel less pain for security is because of Intel is so dominating from a chip vendor point of view, and they drive this PC-based security, including even the data centers and servers and so on. But exactly what happened to IoT is you're not going to see probably a dominant player, at least from now. I look at here, I was listing the gateways, the IoT gateway suppliers. Right? You got STTIs, Oracles, and Intels, and now even Apples. They all have different standards. Not only on software protocol, even the interface. Wi-Fi, Zigbee, Bluetooth Smart, Bluetooth things like so that means that it's difficult to have a table and everybody sitting there and agree, say, oh, all IoT devices will go that. And the reason is because of the application itself is also diversity. So I kind of see here is that whoever gets the killer app, get the volume the production, and they're gonna push that as a more dominant player instead of a consortium of standard gets established for security.
Hey, Brandon, I asked the question whether the low energy, that solution for the IoT, whether there's any standardized type of solution, or still it's really depends on application, and there's no such thing. Can you give your opinion on that?
Okay. Low energy, the lower is better. So I think the application, there's two ways of looking at how to lower your energy cost. One is a very strict convention called scale down. Basically, you take your VDD and you make your system can working on an ultra low VDD, kind of thing. As a designer, I feel there's no standard, but I think what you need to do is a very wide range of frequency and voltage scaling. So your device can consume very little power or energy running at 1 megahertz, but it gets juiced up and running at 1 gigahertz in no time for a particular some sort of computing intensive application. And those are probably in the higher end of wearable, like your wearable, higher end of the IoT, like your wearable device that have that type of requirement. Maybe your sensor node, maybe not. And I've seen a lot of low power, so-called techniques, not really standard, gets proposed in the last 5 to 10 years, geared towards the IoT type of design. But there's really no a standard. Well, there's 1801 is more a very, very specific for digital kind of. IEEE 1801 is to define different power domain to promote the dark silicon. But those I don't consider that is a low power standard. I think the contribution to the low power come from all the different techniques. Some of the digital, some of the analog, some of the system. The cognition layer I display is actually to look at how, from system perspective, from a CPU kind of processing architecture, to say how you're going to be design a microarchitecture that is intrinsically be suitable for lower energy.
Yeah, thank you, Brandon.
Okay.
Yeah, so if you're interested to talk more with Brandon, and he's a great guy to talk, I always like to talk to Brandon, so you can stay for the roundtable, so it's after the event. So we're going to move to the next speaker, which is from the robotic industry. He also have a demo there that he's going to show it a little bit later. So it's Marek Sadowski. He's a robotic expert and sorry for interruption. We're going to present the plaque first to Brandon. Yeah. Sorry for the glitch.